Okay, I got the thumbs up from behind the screen. Okay, so good morning, everybody. I'm Molly, the industrial hygienist with the Environmental Health Services Unit. And like Angela said, I also just graduated from this program recently, so cool to be back here in the nice fancy new lab that was not here when I was in the program. So today I'm going to be talking about overdose prevention sites, more as a case study for talking about occupational and environmental health problems and sort of bridging some of those gaps. I'll admit I'm going to throw a lot of information at you guys, but really the point of this is to show you how we've been thinking through this process of tackling a kind of new and unknown problem and some of the considerations that go into those sorts of things. I mean, this is a little bit uncharted territory that we're really excited to be breaking into. So, excuse me, there we go. So I'll start with an introduction, what overdose prevention sites are, where they're used and why they're important. I'll talk about what to sample for, how we chose that, developing a method to do our samples, and a little bit about exposure limits. Then I'll talk about some specific continuous monitoring and ventilation projects we did. And then finally, I'll talk about some ongoing work that's happening here and, at the BCCDC and elsewhere. And here, actually, come to think of it. So first up is our introduction. And my first poll question. So the question's, what year was the public health emergency around illegal substances declared? It's cool to see all the poll numbers as they come in. So 20, a spread on answers, but the, hold on, get out of your poll. Sorry, I can't get the poll to close out. Okay, so the opioid emergency was first declared in 2016. So really, simultaneously a long time ago, but not that long ago. Since then, the deaths from overdose have generally been on the rise. Although deaths from overdose have started to decrease from peak values, this is an ongoing problem. It's unlikely to go away anytime soon. There were 6 deaths per day from unregulated substances in July, which is the last month that we have this type of data available. This is a shortened graph from the BCCDC Mortality Context app, which I think really better illustrates the gravity of the situation. So not only is illicit drug toxicity the number 4 on this list, but you can see how much younger the people are. The top 3 things above that are 70, 80, almost 90 years old. For illicit drug toxicity, it's 44 years old. So there's a lot of words to talk about this opioid emergency, unregulated substances, illegal substances, illicit substances. It's all kind of time. It's not kind of, it is all tying back to the same thing. What we need to remember is that these deaths aren't all occurring from people seeking and using fentanyl, which is what a lot of people think. This is from contamination of other unregulated substances like methamphetamine, cocaine, heroin, really anything that's unregulated. So with this broad definition of what an unregulated substance is, there's also a lot of ways to use them. There's a 2021 BCCDC harm reduction client survey, which shows that most people who use unregulated substances prefer to smoke them. And in addition to that, the BC coroner's report states that most people who have died were from smoked substances. So, and these deaths were in private residences. So all of this is really pointing to the need for a space where people can use the substances that they would like to use, the method they would like to use under supervision, not in a private space where they can't receive help. This is where overdose prevention sites come in. So an overdose prevention site or a safe consumption site, so OPS, SES, they provide witness consumption services and respond to overdose events. They often provide other services as well, like providing social services or substance use supplies. There was an evidence review by the BCCDC that showed sites were not related to increased crime, but they do decrease public use of unregulated substances and they reduce unregulated substance-related litter. And in addition, people don't actually go very far to use these. Most people are within 1 kilometer of their OPS, which not only all of this eases concerns that some folks have about OPSs, but also points to a need to have a lot of them if people aren't going to be able to travel very far to get to them. So they can take a lot of different configurations. There's purpose-built sites, which is one you can see in that photo there of a booth-style model. There are existing spaces that have been, retrofitted to hold these types of sites. There's trailers and RVs. There's pop-up tents. Sometimes it's as simple as, folding chair outdoors. It doesn't have to have much to provide witness consumption. So this RV is actually from Manitoba, and I thought that it was a really nice photo and a really interesting setup. So the overwhelming majority of these overdose prevention sites are for uses other than inhalation, which is a problem. The fact is, maintaining and managing an inhalation site is just way harder. There's a lot of nuances about indoor smoking and the laws and municipal bylaws about that. Managing an indoor inhalational or even an outdoor inhalational hazard is really hard. I mean, as you guys all know, hopefully at this point, inhalation hazards are kind of hard to manage. And airborne hazard, it could just be difficult and costly to manage for sites that are frankly wanting to spend their money on helping people. You might have seen some reports in the news about unintentional exposures leading to overdose. But a key thing to remember here is that exposure doesn't always equal health harms. So we can think of examples outside of unregulated substances, the idea that dose makes a poison. A lot of this is tied to misinformation. Just touching fentanyl is not going to cause an overdose, as they call it. This is a headline from McGill. You won't die from touching fentanyl. Right on the point. And there was a study of media reports of these unintentional overdoses. Again, I don't want to use scare quotes, but they were never really confirmed to be overdose. A lot of the symptoms were more consistent with things like panic attack or other pre-existing health conditions, right? So, however, that does not mean that we can't say there's no health hazard, right? Severe health outcomes are not the only health outcomes at play here. There's stress. Stress is a big health effect. Worrying about being exposed to these substances is a problem for a lot of folks. People might have personal traumas or other ties to the unregulated substance crisis that makes responding to these types of events really difficult. Even for first responders, just responding to life or death stuff is hard and it's scary and it can lead to mental health problems. So we really can't dismiss that at all. We also don't have a great understanding of the health effects in general. For example, headaches and itchy eyes are potentially associated with this, but they're also potentially associated with a lot of other things. And there's a lot of exposure data, but it's not about unintentional exposures. It's about therapeutic dose for a lot of these substances, which is very different, not only exposure type, but dose level, of course, and use. And finally, the fentanyl, which is, again, the most commonly kind of cited concern. It's not the only player here. We're dealing with really complex mixtures of not just illegal substances themselves, but also any adulterants that are found inside of them. So this is the challenge. We're dealing with a new hazard where we have little to no exposure data. We're working with unique locations that have their own unique challenges. Policies are hard to enact because exposures are usually from emergency situations where somebody is providing response to somebody who has experienced drug toxicity. And sometimes for OPS, there might be these really low-level chronic exposures that are really difficult to quantify and we just don't frankly have a lot of data on. So overall, there's a need to balance the occupational health and public health of these spaces. They need to be welcoming to clients and they need to be available for use, but they also need to protect people who are working in them. So through all of this, I'll be walking you through some of the work we've been doing around and beyond these topics. I'm hoping to give you an understanding of these processes to address this kind of complex issue, and hopefully you learned something interesting. So our first thing was what to sample for, which is the second full question. I don't expect anybody to know this one. I'm just curious what people think. I knew I shouldn't have put it's complicated.
Recording in progress.
So I will not give you a direct answer, and instead I will present to you what the answer is. Oops. I'm trying to close that. Okay. So first thing we did was figure out, what do we sample for? The toxicologist at the BCCDC Environmental Health Unit performed a rapid literature review of what is released when a person is smoking an illegal substance. So there were studies that exist. However, there was not that many of them. They were almost all perfectly pure substances. We're talking like, lab grade cocaine, lab grade methamphetamine, burned at very specific temperatures in very specific ways, put directly into a GCMS or something along those lines. So some of them even had lists of chemicals, but no amounts. Some of them had amounts, but they didn't really tell us about the process that they used to pyrolyze the product. And of course, there's the problem of adulterants themselves, right? So this is not super great for trying to understand our real world scenarios. Even the studies that we did find, there was just not a lot of overlap. There was just a couple onesie-twosie studies for each of the different drugs we were looking for. So the changing supply is an issue besides the adulterants themselves. The substances are getting more potent, and what adulterants are present in the substances also changes all the time. I mean, there's seasonal variability that you kind of expect to see. For instance, the Center for Substance Use, who does a lot of drug checking, they see a lot more psychedelic testing in the summer months when people are going to festivals, right? But even over time since they've been doing testing, there's been a lot of changes. So, for example, the papers we found were from 2015 to 2022. But in the coroner's reports from 2021 to 2022 showed an increase of fentanyl concentration in substances associated with deaths rose from 8% to 17%. That's like a pretty big jump. Or I guess it was 8% 2019, 2020, 17% 2021, 2022. Pretty big jump in a pretty short time. So overall, what we found was that we needed to test for the drugs themselves. To kind of drive this point home, I don't want you to read each of these. That's a lot. But these are just the components that are in unregulated opioids. And you can see that there are uncertain matches, there's uncertain carbohydrates. Even within the others subcategory, there's a whole bunch more things, including no library match, uncertain minerals, uncertain oils. We just don't really know what's in a lot of this stuff. And even when we do, it changes. So we decided to test for the substances themselves, but that gave us a new challenge, which is that there is not a standardized method for this. Most of the standardized methods come from places like NIOSH or OSHA in the USA, but there's not one for unregulated substances. So we have some in-house expertise here, which was very handy. And the OEH lab took on the challenge to develop a test for methamphetamine, cocaine, heroin, and fentanyl. And in addition, they also did bromazolam and atizolam. But to even further drive that last point home, in the short period of time it took for us to do the method development, atizolam kind of disappeared from the supply and bromazolam shot up. So we even had to make adjustments on the fly as we were developing a method to test for these. So the method was developed per OSHA validation guidelines, as these are the ones that WorkSafe BC prefers, and it includes testing for parameters like the effects of humidity, the effects of storage time, and it also looks at details of analysis like detention time and what conditions are needed for the mass spectrometer. It's very, very interesting if you're into lab methods, and it's been published, so that's very exciting. Generally, there were a few out of the ordinary field precautions needed for this, except for one, which is the filter type. So you can see on this graph, this is the percent recovery for different substances using different types of filters. And you can see that some of them don't perform super well unless you silinize them. So salinization is a process that basically is like a chemical treatment on filters that makes them more inert. You can't buy off-the-shelf salinized filters, but pretty much any analytical lab can do it. It's not hard to do. So if you want to do this type of method and you want to have the best possible retention, you want to talk to your lab ahead of time and ask them to salinize your filters for you so that you can have best results. In addition to all this testing in the lab, we brought it into the field and tried to make sure that it would work as expected. We're still working on publishing the results of the field part of the study, but overall we found it worked really well. There's a little bit of ingenuity we had to do with putting the samples inside of client spaces, which is this traffic cone here. So, sorry, I don't have a laser pointer, but you can see inside of the traffic cone, there's a little silver circle. That is the sample, the sampling head. So there was concerns on site about the cones getting tipped over, about people trying to tamper with them, and we can't enter the spaces because of client privacy, right? I mean, ultimately it's a medical issue. So we needed to figure out a really easy, tip-proof, visible way to hand the sampling device over to the people who can go into the space and put it up. So literally what we did was we attached a bottom to a traffic cone, and then we stuck the sampling head out of a hole we put in it, and then they plopped the whole thing down. They didn't have to do anything except for set it down. And it worked really well. And we had a lot of fun modifying cones to do so. But other than that, there was very little extra that needed to be done for the field methods. So now we can test for the substances, but what do we do with the results? For understanding workplaces, you usually turn to an exposure limit. But in BC, there are no WorkSafe BC limits right now. The ACGIH has adopted some TLVs. For those of you who don't know, these are basically just their version of exposure limits, but they're not enforceable. But they're very well respected and very well used. So the ACGIH limits, they have a 15-minute limit of 0.2 micrograms per meter cubed. They have an 8-hour limit of 0.1. And then they also have a surface limit, which there aren't any surface limits that are enforced by WorkSafe BC, but these are still useful for helping develop cleaning guidelines and making sure that your surfaces are not getting contaminated. So these are not legal limits until WorkSafe BC adopts them, which might take some time, but in the meantime, this is kind of what a lot of people who are doing this type of testing are using. Community exposure limits are generally way harder to come by than occupational ones, and there's pretty much nothing out there for unregulated substances. There is a US EPA provisional advisory level, but those are more for emergency response scenarios than they are for these incidental exposures. And in addition, there's some local surface limits for methamphetamine in Australia, New Zealand, and various places in the US, but the acceptable levels, you can see, they range really widely. And that's also tied to clandestine lab cleanup, not again, people using substances, which is a whole other bag of worms to open when you're dealing with clandestine lab cleanups. So there's also other challenges with monitoring. Particularly with surface and community limits, we have to ask ourselves how relevant the limits are to the scenario, and what do the results actually tell us? It's really important to consider this because OPS are run often by nonprofits or sometimes other community groups, and they don't want to spend their money on lab fees. They want to spend their money directly helping people. So taking a bunch of samples willy-nilly really isn't an option. Now, if you do get the opportunity to sample, taking 8-hour work samples, super easy. You put the pump on somebody if you can already own it or if you can rent it, and then you just leave it for their full shift. But peak exposures, those 15-minute exposure limits, they're happening during emergency response. And the amount of substances in the air is going to vary a lot minute to minute based on what people are smoking, how they're smoking, what's the ventilation in the room, what's the size of the room, how long were they smoking for. It's a laundry list of complications. So trying to approximate a 15-minute exposure from longer sample times or from area samples really just isn't feasible. And given that this is an emergency response scenario, you can't stop somebody, put a pump on them, run the tube on them, tape it to them, put your cassette. Every second counts in emergency response. So the question becomes, how are we going to do this? And what are some other monitoring methods we can use for understanding these sites? That's going to move us on to continuous monitoring. So this is my last poll question, which is, I'm just curious about the way that other people have been using continuous monitoring data, because we were doing some pretty interesting stuff with ours. And yeah, I just like to see what people are doing. So interesting. Okay, so some of this complex analysis might be like extra interesting to people, I hope. Because we actually did get to run some pretty interesting, complicated analyses. Well, I should say complicated to me, a hygienist who is not an epidemiologist. This was very easy for my epidemiologist colleagues, not so much for me. One option for monitoring on site that we explored was continuous monitoring. We were able to install continuous monitors at 2 different sites. One was a temporary purpose-built site that was actually indoors and allowed for smoking inside. And then there was one that was an outdoor smoking tent that kind of acted less like a tent and more like a very small indoor space because it had hard walls. Both of these sites have since closed down, but we were still able to get really interesting information from them. The sensors we installed were called air quality eggs. If you're familiar with purple air, it's basically the same thing. They monitor PM1, PM2.5, PM10, pressure, temperature, and humidity, and they upload all this data to a cloud. So, and that's minute-to-minute intervals. So this doesn't give us any information about the makeup of the particulate matter, and we can't extrapolate that at this point in any way. But that doesn't mean that it's not useful in other ways. Just because we can't use this to try to compare anything to a TLV doesn't mean that we don't have use for it. By strategically placing these sensors through the sites, we were able to monitor air movement between spaces. Like I said, we have a very good research team who helped me figure out some of these analyses. And the specific question we looked at, and I'll talk about today, is putting some sensors that were inside of the spaces and outdoors, sort of at a community level sensor as close to the sidewalk as we could get, to try to see if smoke from inside the space was getting outside of the space. And for our indoor site, we were also able to put one inside of where the employees were and use some of that data to check the efficacy of the controls that were in place for preventing the particulate from entering that employee space. There's also other uses that we didn't use them for, but frankly, I could see them being useful for, which is ventilation monitoring on a everyday basis to make sure that your system's running as expected. If your PM levels suddenly change, then you'll know something's wrong with your ventilation. Again, client comfort, super important for these sites. So you can use them for temperature monitoring, for humidity monitoring, and make sure they're places that people actually want to go to. And it can also help maybe signal to people when you might want to do some expensive laboratory tests, good for preliminary testing or just, again, general monitoring to say something's up, we need to explore more. So at the first site, the tent site, our only question was about if it was impacting on local air quality. So this is a little map of the site. Little triangles are where we put a sensor, one inside of the tent, one just like right outside of the tent, and then one further down the street a little bit at a little garden shack kind of area. And those other two were outdoors. So we analyzed 7 days of data, which were not impacted by wildfire smoke. And you could see just from the first day, so this is only day 1 data, so that the graph was a little more readable. The PM levels inside of the tent are just like far and away above levels outside the tent. So the 3 sensors, we called them inside tent, near tent, far from tent. Pretty simple. Just looking at the results on their own without any modeling, you could see, again, the levels are just way higher. Keep in mind that this axis is on a log scale. So even though it sort of looks close, the distance between the in-tent and the outdoor sensors is quite high. So although small, there were some statistically significant positive correlations between the inside and outside tent PM 2.5 concentrations. However, the PM 2.5 near tent was much more highly correlated with the ones far from tent. So the two outdoor sensors were better correlated with each other than they were with anything inside. So we also ran something called the distributed lag nonlinear model, which is what I had our FET help me with. And it looks at the relationship between PM values, taking into account the possible amount of time it would take for the particulate to go from the tent over to our other sensor that was far away. So the results of this modeling is in table 2. And you can see there's just really little influence of in-tent levels on the outside of tent levels. The inside tent and far from tent results were not statistically significant. And even if they were, you can see these R-squareds are like so small. So it really suggests that the impacts from the tent are likely to be minimal, even close to the tent itself. In sum, the measurement data suggests that PM 2.5 concentrations inside the tent are not substantively impacting PM 2.5 concentrations outside of the tent. Of course, there's a major limitation to this, which is that we only collected the data for a week in August. Who knows how non-August type weather might affect this data. And again, we just want to make sure that it's very clear to people that like PM data does not equal like hazard data. Like we don't have anything on this that talks about any specific substances at this point. So for the second site, which was the indoor site, we installed even more sensors. This one worked under a dilution ventilation principle. I kind of tried to draw the big vents here in the inhalation room. That's what those big silver U shapes are. Basically, these sucked a large volume of air out of the inhalation room. It ducted it into the HVAC room where it was filtered and then exhausted out the roof through some stacks. So the workers occupied the office adjacent to the inhalation room so they could monitor people inside the inhalation space. So there were controls in place to keep smoke out of that office, but also to keep in mind there's a door and 2 windows between the office and the inhalation room, which could be opened either to provide emergency care or if somebody needed some substance use supplies or needed a advice or to talk to somebody or whatever. People could open those windows to pass through what was needed. So there's a lot of reasons that monitoring here was more complex. First, we had workers, which were very close by. Second, we had inside of the inhalation room, there were holes directly to the outside cut into the room near the ground. So this was done to help act as makeup air so that air was pulled up a lot easier inside of the inhalation room. But that meant that if there was wildfire smoke, our results were going to be very unrepresentative. So we had to make sure we were thinking about that. We also, the air was being filtered before exhausted, which isn't necessarily a complication, except for that meant that we wanted to put a sensor on the roof, which was a little bit challenging. The site has operational and non-operational hours, so we needed to make sure we were considering those separately. And then finally, because we were thinking about community exposures here as well, we put one outside the employee entrance there, which is as close as we could get to the sidewalk without, a plug-in source. So in sum, we've got our office sensor, we've got one inside of the inhalation room, one at the roof above the HVAC room, and then one outside of the employee entrance, which acts as our community level sensor. For this one, we were able to get about 2 months of data, also during the summer months. We again focused on PM 2.5. Again, this is a log scale graph. You can see overall PM 2.5 values within the inhalation room were orders of magnitude higher than those in the office, at the employee entrance, and on the roof, especially during operating hours. There's some differences in the on-off hours, which is really interesting. And then overall PM 2.5 concentrations in the inhalation room didn't quite get back to background levels but we think that's pretty easy to explain, which is that people were using the room right before closing, and then as soon as the site was closed, they turned off the ventilation. So this is a visual that shows the Spearman's correlations for the different sensors during operating and non-operating hours. Closer to 1 is better correlation, and for reference, a value of 0.1 is pretty small, so not a super meaningful correlation. And for this graphic, darker blue equals closer to 1. So overall, you can see relationships between sensors are stronger during off hours than they are during on hours, and then which is likely due to just they're all at background. That makes sense. And the inhalation room is really not well correlated with other sensors during operating hours. It's also important to point out that not only is the relationship between the employee entrance and inhalation room near 0, the p-value is non-significant. Here's some numbers, which we did for a linear regression model, which is another way we were trying to make sure we were talking about how all these are different, or how all of these different sensors were related to each other. The key is here, the inhalation room and employee entrance have a negative relationship with an extremely small R-squared, and the R-squared relationship is lower during operating hours than during non-operating hours. So, in sum, there were persistently higher PM2.5 levels in the inhalation room. There was a non-significant correlation and negative linear model between employee entrance and inhalation room, and stronger correlations between the roof and the entrance sensors, those two outdoor sensors, which suggests the inhalation room was not impacting on community level PM levels. And finally, the controls in place are reducing the PM2.5 levels in the office when you're compared to the inhalation room. You can see that through our models and also through the correlations. So like with the tent data, we don't really know what's in the PM2.5, and we also did this during the summer, so there are a couple limitations to it. So with all of that in mind, let's talk a little bit more about ventilation. Throughout all of my work on this, we've learned that there's so many factors to consider, and one of the biggest considerations is client needs. Some clients prefer to use in small groups, and sort of like in a social gathering situation. Some prefer a solitary model because it can prevent, harassment or undue socialization that they aren't particularly interested in. Either way, the needs of the community have to be considered to open a site like this, or else people just aren't going to use it. Given that an inhalation site, again, controlling an airborne hazard, ventilation is crucial. There's no one-size-fits-all model. There's no correct ventilation method except for the one that works. So some potential ventilation methods have been booth styles with their own individual ventilation systems, dilution ventilation, which again is what was used at that site that I just talked about. Having outdoor sites is of course a form of ventilation, but then how do you quantify that? How many people can be inside of one tent? How many walls can you put up? Things like that. The photo here, you can see that it's one of the tent sites that's here in Vancouver. And then this is a photo of the inside of the indoor inhalation site that I was talking about earlier. So with many different types of buildings that could become an OPS and SCS, how would you retrofit them to be good? I mean, old buildings, it can be just cost prohibitively expensive to retrofit them to work. So the kind of last consideration with this is that the source of contamination, when we think industrial hygiene, usually it's a container of chemical or a stationary process that's happening. But that's usually pretty consistent. But here again, we're talking about people who might want to move around or who are using in different ways, who are using different substances. It's pretty complicated. The last major consideration is, of course, the environment itself. When you're having something like a tent site or the one that had those big holes on the side of the wall, how are you going to manage during extreme weather? How are you going to protect people from wildfire smoke, from extreme heat, or from extreme cold? Given all of this, the temporary inhalation site that I talked about earlier wanted to know if they could turn down their ventilation. So to utilize their dilution ventilation, they had to have their ventilation up so high. It was really noisy. It kind of created these drafts. It pulled in a lot of outside air, which meant that in the summer it was really hot, in the winter it was really cold, and it was just kind of hard to hear. So they really wanted to try to turn it down so that it would be comfortable for people who wanted to use it. To do this, we decided to evaluate their ventilation system. We went to the site after hours. We filled the room with smoke via a smoke machine. We adjusted the ventilation at a couple different rates, and then we tracked the PM levels in the inhalation room with the dust track. The data analysis was looking at decay rates for the different ventilation settings, and controlling the ventilation was with these little knobs, which you can see here. very imprecise. There was one per fan and there were 3 fans. So we couldn't really figure out the air exchange rates on the fly because we had the outdoor air to consider. We had a bunch of different vents. We didn't have a lot of time. So we tried to approximate it based on the percentage of the current level. So 100% is what it's usually running at. 80% is in theory 20% lower based on knobs, but as you'll see, that was really imprecise, and we will talk more about that later. These are the equations we used. So we analyzed the air changes per hour and the rate of decay. While the site had measured air changes with air velocity measurement tools, like putting actual velocity calcs up to the vents, that doesn't always give you an accurate understanding of how the contaminants are moving out of a space. If the ventilation isn't strong enough to pull contaminants all the way up, then they might settle. There's also places where it might get trapped, like light fixtures, or if there's like a big statue in the room or something along those lines. So that is why having the smoke was really helpful, because it gave us a pretty accurate representation of what the air changes are actually like in that space. So generally this first equation, which is the air changes per hour, uses CO2 as a testing gas, but here we use PM. C is the concentration. For ambient levels, we just use background present in the room. T start is the last time our data was at 150 milligrams per meter cubed, which seems very complicated until you remember that is the maximum reading on a dust track. And our T end was, again, it's going to sound complicated, the time at which the first instance of PM levels reached the lower 5th percentile of the data distribution. And the reason we couldn't use just return to background is because when we actually looked at the data, we didn't quite get back to background for every trial. That's just a matter of you can't see PM, and we tried our best, and we only had 3 nights to do this. So the second equation is for smoke clearance, which is the decay rate. So we use a linear model to figure this out. T is the time in seconds, C is the y-intercept, beta is the regression coefficient, and PM is any of the PM measurements. The beta and C were estimated by a model using ordinary least squares. So these are our actual air exchange rates at each of the percentages I tried to estimate. And these are by particulate matter size. So the site generally operated around 70 air changes, but once I changed it down even a little, you can see there was pretty dramatic shifts. And again, you can see how similar the 80 and 60% are. Those knobs are very fiddly. So overall, a key takeaway here is that there's not a huge difference between the different size bins. And that's important to know, because if there was a big difference in size bins, we would need to make sure that whatever ventilation we're doing is adjusting for, or is mostly evacuating the bin that we're most concerned about. And in addition, the kind of nice thing about that is we could aggregate all of our data when we did our statistical analysis, and we had even more statistical power because we had so many more data points. This is an example of the model decay rate. It's the percent reduction per minute of PM2.5 at the different rates. Now, it seems like 60% is slightly better than 80%, but remember, 60% was actually slightly more air changes than 80%, so just keep that in mind. Well, overall, really the important thing to remember here is that the difference between 100% and 60%, or approximately 66 to 52 air changes, wasn't really that much. So that doesn't mean we can just turn down the ventilation, right? There's a lot of other things that needed to be factored into that decision. It would make the space quieter, of course, but again, PM doesn't tell us concentrations of what's actually in the air. So we weren't really sure if turning down the ventilation would result in any sorts of overexposures. However, the site closed before we could do any further testing. So overall, there's still a lot to be done, which leads me to my last section, ongoing work. The BCCDC, WorkSafe BC, and health authorities have linked together to form a controlled substances exposures committee, which is developing guidelines to try to talk about a lot of these needs. The outdoor overdose prevention guidance is in its last stages of approvals, which is really exciting. And then we're working on some acute care guidance right now. And then we're going to move on to other settings too, like housing or sort of community level exposures as well. UBC, and specifically Hugh, who's right here, has been submitting a lot of grants with us, and we're working on figuring out minute-to-minute exposures when folks are using substances, and then we're also exploring a very specific type of like temporary OPS solution, which we're really excited about. But of course, we're not the only ones doing this. Great. There are other Canadian jurisdictions that are working on these types of things. The first inhalation site was actually opened in Lethbridge, so it has since closed down, but more to show other places are exploring stuff like this. There's also, of course, the US. They're always putting out lots of stuff. There's working groups and committees at organizations like AIHA that are trying to address different aspects of use at workplaces, and of course, the academic research community as well. So, in conclusion, there's still a lot of unanswered questions about unintentional exposures, especially for workers. So we've had to start from scratch, looking directly at unregulated substances that, even if they don't have an exposure limit, we've kind of figured out ways around that. We've tried a bunch of different sampling types at a bunch of different sampling locations, and we've applied a lot of principles we're already familiar with, like different ways to measure ventilation, to try to solve some of these problems. Again, working with these sites is crucial. We need to make sure that we're understanding what the community needs are and what the worker needs are simultaneously, and we need to make sure that we're doing so without breaking the bank, because again, money is a problem, always. And of course, even though we've come far from where we started, there's a lot to be done, and urgently so. I mean, you know, even if overdose deaths are declining, that there's still far too many. So we do still need to do a lot more work on this right now. And I have a little sources slide if you're curious to learn more, but that is all.